Arithmetic coding is discussed in this segment, which addresses some of the shortcomings of Huffman encoding. According to it, a unique identifier, or a tag, is generated for a particular sequence of symbols without the need to generate all possible code words for sequences of the same length, as were the case for Huffman encoding. We show how this tag is generated by mapping each symbol to the real line segment from 0 to 1 and keep zooming into the segment as more and more symbols are observed. Arithmetic coding is also suitable for dealing with short dictionaries, as is the case with binary fax images, and also for taking context into account, therefore locally changing the probability of the symbols. Because of this, it's the code chosen by the Joint Bilevel Image Processing Group, JBIG, a group of experts that established a standard for the progressive transmission of bilevel images. The basic principles of JBIG are also described in this segment. So let us now have a closer look at this material. We saw that it is more efficient to generate code words for groups or sequences of symbols instead of generating code words for individual symbols. And we call this block coding. In terms of Huffman block coding, though, we saw that if we want to encode a particular sequence of length m, then we have to find the code words for all possible sequences of the same length. And this clearly has the major disadvantage that the size of the alphabet grows tremendously. So if I have an alphabet of size n and extend the source by m, then the new alphabet of the extended source has size n to the m. We would like clearly to address this, and the way to address it is through arithmetic coding. So with arithmetic coding, we can assign a code word to a particular sequence without having to generate codes for all sequences of that same length. The way it is done is by finding a unique identifier or a tag for this particular sequence we want to encode. And this tag corresponds to a binary fraction which becomes the binary code for the sequence. So we would like to separate the generation of the tag and the generation of the binary code. We'll just discuss at some high level how the tag is generated, but we will not get into any of the details of how the code is generated. It's a rather complicated matter. One possible set of tags for representing sequences of symbols are the numbers in the interval 0 to 1. Because there are infinitely many real numbers in this interval, it should be possible to assign a tag to any sequence we are interested in. In order to do so, we need a function that will map sequences of symbols into the unit interval. Such a function is the cumulative distribution function. So we are given an alphabet here with little m symbols, and here are the associated probabilities. We know that a random variable maps the outcomes of an experiment to the real line. So we'll use this random variable here, x, that will map the outcome of the experiment, the elements of the alphabet here, the symbols, into the index of the symbol I. So now, given the probabilities of the source, we're given the probability density function of this random variable. So the probability that the random variable is equal to I is simply the probability of the symbol AI. And of course, we can have the cumulative distribution function, f of x of I, the sum k1 to I of this probability that the random variable is equal to k. With this assignment, the main idea behind the tag generation is to reduce the size of the interval in which the tag resides as more and more elements of the sequence are received. So we partition the unit interval into sub-intervals of this form. So this is the line from 0 to 1, and symbol A of 1 resides in this interval from the cumulative at 0 and the cumulative at 1, and more specifically A of I belongs to this interval, so it's closed at the lower side and it's open at the upper side. So the appearance of the first symbol in the sequence restricts the interval containing the tag to one of these subintervals. So let's assume that the first symbol is A2. Then the tag will be in this interval here, and this subinterval is partitioned in exactly the same proportions as the original interval. So each succeeding symbol causes the tag to be further restricted to a subinterval that is further partitioned in the same way. So let's look at an example where hopefully this idea will become even more clear. Let us now look at a simple example of a tag generation. We're given a source with this alphabet, and here are the associated probabilities of the symbols. Based on what I just discussed in the previous slide, through the assignment of a random variable, we can find the cumulative distribution function of that random variable. And we have that f of x1 equals PA1, f of x2 equals PA1 plus PA2 equals 0.8, and f of x3 equals 1. So with these values of the cumulative distribution function, we take now the segment between 0 and 1 and divide it. Here is f of x0, here is f of x1, f of x2, and f of x3. So A1 resides in this interval, A2 in this interval, and A3 in this interval. Let us assume that the first symbol we observe is A1. This means that any number in this interval between 0 and 0.7 can serve as the tag to uniquely identify A1. I take the 0 to 0.7 subinterval and subdivide it proportionally to the original probability, so 70% of it is occupied by A1, 10% by A2, and 20% by A3. If the second symbol we observe is A2, then the tag resides in this interval. I take this interval, subdivide it proportionally to the original probabilities. If the third symbol I observe is A3, then the tag resides in this interval. I can further subdivide this, and so on and so forth. So if the sequence we observe and we want to encode is A1, A2, A3, then any real number in the interval 0, 5, 4, 6 to 0, 5, 6 can serve as the tag to uniquely identify this particular sequence. It is clear that I'm looking for an identifier just for this particular sequence and not for any three-symbol element, as were the case with Huffman encoding. Typically, the middle point of this interval is chosen as the tag, and also there are recursive ways to evaluate, to compute the tag, as well as to compute the boundaries of each of the subintervals each time I take a subinterval and further subdivide it, and so on and so forth. So this is the basic idea of how a tag is generated. Let us see with a simple example how to decipher the tag and find out what is the sequence that was encoded. So we consider again the same source as shown here, and we are given that the tag is equal to 055. So we want to find again what is the encoded sequence. We have, of course, in addition to the tag, be given the information of the number of symbols in the sequence, and we're given that there are 3 symbols that were encoded. The main idea in deciphering the tag is to mimic the encoder so that we decode the tag, decipher the tag. So we take this information about the source, we take the segment between 0 and 1 and subdivide it proportionally as we did before. Now, clearly the tag resides in this interval. If you recall the steps we followed while encoding, the first observed symbol sets the stage in some sense to where the tag is going to belong. In other words, the tag cannot belong to a segment outside the initial segment, because in each step we are subdividing the initial segment. So the fact that the tag for this particular example belongs to this interval means that the first symbol that was encoded is the symbol A1. So we mimic the encoder, take this interval, subdivide it proportionally, and now we observe that the tag resides in this interval. Therefore, the second symbol that was encoded was A2. Mimic the encoder, subdivide this, we see that the tag belongs to this interval, and therefore the third symbol that was encoded, and we're decoding it now, is A3. So in summary and conclusion, the decoded sequence is A1, A2, A3. We would like to briefly compare the performance of arithmetic coding and Huffman. As we already saw, this is the relationship the Huffman rate satisfies as a function of the encoding block size capital N. The related relationship for arithmetic coding is given here. By comparing these two expressions, it seems that AC does not have as good of efficiency as Huffman coding, since 2 over n here goes to 0 slower than 1 over n. However, as we discussed, Huffman coding suffers from the explosion of the size of the dictionary, and in practice it is arithmetic coding that achieves rates close to entropy. Of course, we did not discuss how the tag is encoded. It should be clear that as the size of the message n increases, the precision of the tag increases. We need to represent a real number with a lot of decimal points. Scaling and incremental coding are used to address this issue. If the tag is in the 0 to 0.5 interval, for example, it's clear that it's restricted to stay there. Therefore, the 0 to 0.5 range can be scaled back to 0 to 1 range. By doing so, we lose the most significant bit, which, however, was already sent to the decoder by signaling which half of the line we are using, and this is called incremental coding. I want to demonstrate with a simple example the benefit of taking the context of a symbol being encoded into account when encoding an image, and then using multiple coders, each of them adapting to the statistics of this context. The words context and content are both used in image and video processing, but at times they're confused. By what I'm describing here, the content of an image is taken into account, but we are adapting the coder to the context of the pixel or the symbol in general being processed. So it's also content adaptive, the processing I'll describe next, but to be more precise, we are looking again at the context of the pixel being encoded. This actually will become much clearer in the next few slides. We will also talk later in the course about other examples of content adaptive processing. So we are looking at a document which has these probabilities of black and white pixels. The white pixels dominate, which typically is the case with a lot of documents. We know how to find the entropy of this source, and it's equal to this so many bits per pixel. So based on what we've learned, if the model here that was used to find the entropy of a discrete memoryless source is accurate in describing this document, then we know that we cannot find a coder that can have a performance below entropy. Now, we divide the document into two regions. Region 1 is the larger one. It includes 80% of the pixels, and region 2 includes the remaining of the pixels. Region 1 is dominated by white pixels. 95% of them are white. So if we find the entropy for region 1 is equal to the number shown here. Region 2 is dominated by black pixels, and the corresponding entropy is shown here. Now, the total entropy of the source is the weighted sum of the two entropies of the regions, where the weights are proportional to the number of pixels in each region. So in other words, the total entropy is 0.8H1, 0.2H2, and this is the resulting number. So what we see is that by dividing the document into two regions, the entropy has been reduced to almost a half of the original entropy, and therefore the use of multiple coders which adapt to the context of the symbol being encoded is beneficial. And this same idea has been used extensively, of course in a more refined form that I will explain later, when arithmetic coders are used. I should mention here that this is a case of a small alphabet, of a source with a small alphabet and skewed probabilities of symbols. So we know that for this case, Huffman coding has low or problematic performance, while a source like this is very suitable for arithmetic coding. A case where context-adaptive arithmetic coding is used is in the JBIG standard. JBIG actually stands for Joint Bilevel Image Processing Group. So this is a group of experts that established a standard for the progressive transmission of bilevel image. JBIG is therefore a combination of a progressive transmission and a lossless coding algorithm. Arithmetic coding again is used for the lossless coding part, and arithmetic coding is suitable for the use of multiple coders since they all use the same machinery. They simply use a different set of probabilities. So JBIG encodes the pattern of pixels in the neighborhood of a pixel being encoded, that's the context, to decide which set of probabilities to use in encoding a particular pixel. So it uses these two neighborhoods. Each of these neighborhoods has 10 pixels. So I'm interested in encoding the pixel at location X, and I look at these 10 neighbors. Here they extend over 3 lines. Or I use this pattern, so for encoding this, I look at these 10 neighbors that extend only over 2 lines. Since there are 10 neighbors, there are 2 to the 10 or 1024 different contexts or different coders. Actually, JBIG is using as many as 496 different coders when we deal with a high resolution image. A here is a floating member of the neighborhood, and it can be placed anywhere in the image to possibly uncover specific structures in the image. We also notice that the shape of the neighborhood allows recursive computability. That is, the neighborhood includes previously encoded pixels, and therefore these pixels are available to both encoder and decoder so that they can synchronize their operations. So if we look at a particular example of this first neighborhood, so we want to encode 0, and we look again at these 10 neighbors, we see that in this particular example there are 70% of the pixels are black, the zeros, and 30% of the pixels are white, corresponding to ones. So an arithmetic coder that works with this probability of symbols is going to be utilized in encoding the value of the 0. Similarly, if this were the situation of the neighborhood, so in encoding the value of 1 here, in this particular case, 60% of the pixels are black and 40% white. So an arithmetic coder utilizing these probabilities will be utilized in encoding this particular pixel value. The idea behind progressive transmission is to represent an image at various resolutions. So a low resolution version of the image is first transmitted to destination. If the recipient is interested in this image, might request a higher resolution version of the same image to be transmitted. It's the same idea of the thumbnails we see on the web. It's a tiny image. If interested, we click on it and we see a higher version of the same image. Now, one of the challenges when we deal with binary images is how to downsample them. JBig allows a 2x2 factor downsampling. So if we have 4 pixels here, we want to replace them by 1 pixel. So if I take the average of these 4, the average is clearly 1/4. So one might think, okay, we could compare this to a half. Since this is less than a half, then this should be replaced by a 0. But clearly we have a difficulty when we have this situation, because the average of the pixels is half, and therefore it's not clear how to resolve this situation. If the downsampled version of this 4x4 neighborhood should be a 0 or a 1. To address this, JPEG is considering a scheme as shown here. So we are interested in finding the low resolution value of x, and instead of using just the 4 neighbors at the higher resolution, right, we want to find how to replace these 4 values at higher resolution by 1 value. We are also utilizing additional values at higher resolution. These are the small case letters, as well as the already previously computed values of the low resolution image, the capital letters. Then the standard proposes the evaluation of this formula here, where again all these labeled pixels at low and high res are taken into account, and if the value of this expression is greater than 4.5, x is equal to 1, otherwise x is equal to 0. I guess it's always a question, where did this expression come from? And very often in standards there's a lot of thinking and experimentation that takes place before something is standardized. So this at the end, if one stares at it and tries to reason, makes sense, and this is how it's implemented in the standard. In progressive transmission, the decoder has already received the low resolution image, and of course this image is available at the encoder, and therefore the low res values can be used as context when we perform arithmetic encoding of the high res image. The advantage now is that the received low resolution values are in the past with respect to time, but include information about the pixel that is being encoded, as well as future values with respect to space of the high res image, and therefore the context can be more informative in this case. Here are the 4 context templates that are utilized by JBig. X again in red is the pixel value being encoded. We see that past values of the high res image are used, and these big O's are the low resolution pixel values. A again is this floating location of the pixel. So you see, for example, that in computing this O value of the low res, the value we tried to encode of the high res was taken into account, as well as future values, and this is the case for all these 4 low resolution pixels. So in this template, it's this low resolution value that has included the value that we try to encode of the high resolution image. Since we have to include 2 bits to indicate which of the 4 context templates we are using, we have therefore used 12 bits, and therefore there are 2 to the 12, 4096 different contexts.